Welcome to AP Biofine with Dr. D. This presentation on Hardy-Weinberg equation and how to solve Hardy-Weinberg problems is in addition to Mr. Anderson's video. There is going to be a lot of repetition, but I find that students are often struggling with solving Hardy-Weinberg problems, so it bears repeating. So let's get started. So what is Hardy-Weinberg? What is it all about? It's an equation which is meant to mathematically describe a naturally occurring phenomenon, and as such is a type of model. To explain Hardy-Weinberg, let's look at a hypothetical trait which is determined by a single gene, and the gene exists in only two different forms. The dominant allele is capital M, and the recessive allele is little m. Okay. There are a total of 1,000 alleles for this gene in the population. If we know the number of dominant alleles, so if we add the number of dominant alleles to the number of recessive alleles, we should get 1,000, right? If the total is 1,000, when we add the number of dominant to the number of recessive alleles, we should get 1,000. So what is the frequency of the dominant alleles and what is the frequency of the recessive alleles? If we call the frequency of the dominant alleles P and the frequency of, then the frequency of the recessive alleles should be, is going to be, we're gonna call it Q, okay? So P would be the number of M, capital M, over 1,000, right? Because 1,000 is the total. So number of M over 1,000. And Q would be the number of little m, and I just realized I misspelled number, over 1,000, okay? Now, P plus Q, if we substitute for what we just wrote, would be number of dominant over 1,000 plus number of little m recessive over 1,000, or it could be big M plus little m over 1,000. And since we already said that the total number of alleles is 1,000, so when we add big M to little m, you would get 1,000. It's 1,000 over 1,000, or it's 1. So this explains why when we add the frequency of the dominant allele to the frequency of the recessive allele, assuming we only have two alleles, of course, for this given gene, we should get 1, okay? So this is a very important equation. P plus Q equals 1, always, no matter what, okay? So here we mathematically represented the observation that the frequency of alleles should add up to 1. In other words, if you have 70% of the dominant allele, then the recessive must be 30 because it has to add up to 100, right? 100%. Let's make another assumption. In the population of 1,000 alleles, we have 500 dominant and 500 recessive alleles. So if we were to cross two heterozygous parents, the Punnett square would look something like this, right? One parent was going to give you two different gametes, the other parent is going to give you two different gametes. And then once you make the Punnett square, which is divided into 4 equal squares, you will see that 1/4 of the offspring should be homozygous dominant, 1/4 should be homozygous recessive, and 2/4 or 1/2 should be heterozygous. Now I want you to notice that the square is divided into 4 equal smaller squares because the number of alleles equal. So we have 500 dominant and 500 recessive alleles. Now we do Punnett square for a single pair, right? Now here we did a Punnett square for the population, which is not exactly right, but a Punnett square is simply a tool to calculate probability. Remember, this is just math. This is calculating probabilities. A Punnett square is a way to calculate probability. Another way would be to use the multiplication and addition rules, if you remember. And we can do that here as well, right? So the probability of getting a homozygous dominant from the Punnett square and from multiplication rule is 1/4. Why is it 1/4? Well, we know the frequency of the dominant allele is 0.5. And to be homozygous dominant, you have to have one dominant allele and another, right? So we're going to do 0.5 times 0.5, or that's 0.25 or 1/4. 1/2 times 1/2 is 1/4. Similarly, you can calculate the probability of getting a homozygous recessive. Now, to get a heterozygous, if you remember, especially how Mr. Anderson explained it in his genetics video, you can do dominant recessive. That's one way to get a heterozygous, or you can do recessive dominant, which is another way to get a heterozygous. So depending on which allele is contributed by which parent, you can get it two different ways. And for that reason, we have the probability of being heterozygous one way is 1/4. The probability of being heterozygous the other way is also 1/4. And since either or could give you heterozygous or means plus, we add them. So it is 2 times P times Q, right? P is the frequency of the dominant allele, Q is the frequency of the recessive allele. Okay. So now that we have established that P squared represents the chance of getting a homozygous dominant, right? The frequency of the dominant times the frequency of the dominant will give you homozygous dominant. The frequency of the recessive times the frequency of the recessive gives you homozygous recessive. That will be Q squared. And we can get PQ, dominant times recessive frequency, which is a heterozygous, 2 ways, which means the frequency of a heterozygous individual is 2 times PQ. Okay. Now, if you add those numbers, they should add up to 1. Why? In a population, you're either homozygous dominant, you're homozygous recessive, or you're heterozygous. There's no fourth option. So when you add all the frequencies up, that should add up to 1, correct? So after all, there's only 3 possible genotypes. Okay, so the number of heterozygous dominant over total plus the number of homozygous recessive over total plus the number of heterozygous over the total should give you 1. Or another way to represent this is that P squared plus 2PQ plus Q squared equals 1. And again, P squared is the frequency of homozygous dominant, Q squared is the frequency of homozygous recessive, and 2 times PQ is the frequency of heterozygous individuals. So when you add them all up, they should add up to 1. Okay, so let's change our assumption. What if the population of 1,000 alleles, there's 700 dominant and 300 recessive alleles? Now, if we were to cross 2 heterozygous parents, the Punnett Square, remember how Mr. Anderson explained it, should now not be divided in 4 equal squares. Why? Because there's more of the dominant than there is of the recessive. So see how the lines were moved to reflect that you have a higher chance of getting a dominant allele than a recessive allele, because the dominant allele is 70% versus 30% for the recessive allele. So now, if we're using the multiplication rule, you can get a dominant individuals by getting 2 dominant alleles. The frequency of the dominant allele is 0.7. So 0.7 times 0.7 will give you 0.49. Okay, so we multiplied the chance of getting the capital M gamete from mom with the chance of getting the capital M gamete from dad, right? That's 0.7 times 0.7. Or P times P, or P squared. In other words, P squared represents the chance of getting a homozygous dominant, or the frequency of the homozygous dominant individuals. We can make the same calculations for the homozygous recessive. And again, I would like to point out that these are probabilities. If the frequency of the dominant allele is 0.7, then the probability of getting a homozygous dominant is arrived by saying, well, what's the chance the dad has the dominant allele? Well, the chance is 70% or 0.7, because that is the frequency of the allele in the population. The chance of the mom contributing a dominant allele is also 0.7, because that is the frequency of the allele in the population. So when you multiply these 2 chances, right, because we want to have the allele from mom to be dominant and from dad to be dominant, and means multiplication, you get 0.49. And you can apply the same principle to the homozygous recessive. What's the chance your dad gives you a recessive allele? 0.3. Why? Because there's only 30% of this allele in the population. What's the chance of your mom giving you a recessive allele? 0.3. And since in order to be recessive, you have to have both alleles present, both recessive alleles present, you multiply 0.3 by 0.3 and you get 0.09. So the probability of having homozygous recessive individuals is 0.09. Okay, now let's look at the heterozygous individuals. Okay, what is the chance of your dad giving you, actually, let's do it the other way around. We can either do it by looking at the Punnett Square, or you can do it with multiplication. So what is the chance of getting the dominant allele from mom? that chance is 0.7 because that is the frequency of the dominant allele in the population. So now that you have the dominant allele from mom, you need to get the recessive allele from dad in order to be heterozygous. So that means that we need to multiply 0.7 to 0.3, right? Because the recessive allele is frequency 0.3, and we get 0.21. Okay, now you can also be heterozygous if dad gives you the dominant allele and mom gives you the recessive, which again gives you 0.7 times 0.3. And that also gives you 0.21. Since you can get it either this way or that way, or since we have an or, now we add. That's the addition rule, okay? So we gotta add 0.21 to 0.21, and it comes out to 0.42. Or you could just write it as 2 times 0.7 times 0.3, or 2PQ, okay? That is the frequency of the heterozygous individuals, okay? All right, now let's look at a totally wacky approach to the Hardy-Weinberg equation. And that it may seem wacky, but remember what I've told you. Every equation, whether it's a math equation, equation in chemistry, equation in physics, is really a model to describe a natural phenomenon. So the mathematical simple algebraic transformations we're going to do today are really reflecting what I just told you. The multiplication, the addition rules to calculating probabilities. But let's just approach it in a completely wacky way. So we know that if we have 2 alleles in a population for a given gene, the frequency of one and the frequency of other have to add up to 1, right? It doesn't matter what else is true or not true. If you have 15% of one allele, then the other allele must be 85% because they add up to 100. So frequency is not percent, right? So P plus Q equals 1. So 0.15 plus 0.70, no, 85 should equal 1, correct? So P plus Q equals 1. We know that. Now let's have some fun with this. So if X equals Y, we also know that X squared should equal Y squared, right? That's a rule in algebra. So what if we square P plus Q? Well, then we should, it should read like this. P plus Q squared should equal 1 squared, but 1 squared is 1. So really P plus Q squared is 1. And if you expand P plus Q squared using algebraic rules, you get P squared plus 2PQ plus Q squared, okay? So we just transformed the P plus Q equals 1 equation to the Hardy-Weinberg equation. Voila. Okay, by the way, the Hardy-Weinberg equation will be given to you on the formula sheet, so there's no need to memorize it. You just need to understand what each of the components of the equation represents. So if a population is not in a Hardy-Weinberg equilibrium, it is evolving. And it's important also to understand that the population might be in Hardy-Weinberg equilibrium for some loci and be evolving at others. When a population is evolving, doesn't mean that all genes are changing. It could be one or a few genes that are evolving while others are in equilibrium. So whenever we do Hardy-Weinberg equilibrium, we always apply it to a single locus, a single gene. And you need to remember that the Hardy-Weinberg equilibrium is an ideal situation. So in order for a population to be in an equilibrium, all of the following conditions need to be met, all right? All of them, not one, but all. No mutations are happening. There's random mating, so there's no sexual selection going on. There's no selection, there's no selective pressure. The population is very large in size, so there's no genetic drift, bottleneck effects, and so on. So the population must be large in size. And there is no gene flow, there's no migration. All of these conditions need to be met for us to say that the population is in Hardy-Weinberg equilibrium. Okay, and this is the end.